Example 5.1a. A parallel plate capacitor has a circular plates of 8.20 centimeter radius and 1.30 millimeter separation. Calculate the capacitance and the charge on the plates when 120 volts is applied. B, there's a second part, but let's go through the first part first. So, and I'll come back and we'll look at B. So here's the first part that we want to look at. So let's sketch the situation. So we have circular plates. So the first thing that we should start here is that we should sketch the plates. So I imagine that I have plates that look something like this. And they're going to have just a tiny thickness. And then, you know what? No, let's just leave it. And then, so this will be my top plate. Then right below that, I have a second plate. And I should copy this and then put this back in. So you could see that I have two plates here. So when I think about these plates here, I imagine that I have an upper and a lower using the same colors that I've been doing before. And then I have a wire that's coming in and one that's down at the bottom. So here's my wire. And then what you're seeing here is that this guy is going to be, it's going to have an area A. And then I have a plate separation. So between here and here, this is going to be my plate separation. Little d. So what are the characteristics of the capacitor? So the capacitor's characteristic are its permittivity, and we're using that of air, and its geometry, which is the geometry of area and plate separation. So when I look at the values, I then see here that I have epsilon for air, and this is going to be kappa times epsilon of the vacuum. And what we're seeing here is that for air and vacuum, it's very, very close to 1. So if I now multiply these two together, I then get a value, of course, to this many sig figs of 10 to the minus 12 farad per meter. Again, that's my dielectric material. Now, when I look at the plate separation, it's 1.30 millimeters, but we got to convert that into meters, which will then be 0.0013 meters. And then I look at my area, which is then going to be pi r squared. But when I look at my area here, I know that the radius is 8.2 centimeters. So in other words, this has to be pi of 0.082 meters squared. And so when I look at this value, I'm going to get 0.0211 meters squared. So now I have my material, dielectric material, and I have my geometry set up. So now I can go in and calculate the capacitance. So if I calculate the capacitance, we then say that the capacitance of this capacitor is then going to be epsilon naught, the area divided by that. And so then I'm going to write in 8.85 times 10 to the minus 12 farads per meter times my area, which is 0.0211 meters squared. And then I'm going to have 0.0013 meters. And when I compute that, I get a value of 1.44 times 10 to the minus 10 farads. And this is my capacitance for this circular parallel plate. Now, the amount of charge still comes from the capacitor equation. The amount of charge on the upper plate, let's say, which is the same as the lower plate, is then going to be given by the capacitance of charge divided by the voltage, or we could say that then the charge is the capacitance times the voltage applied. So in this case, it's going to be 1.44 times 10 to the minus 10 coulombs per volt times 120 volts. And again, I didn't cancel the units out before, but you could see that these volts canceled out. And before, I would have had that meters cancel out with that meters. So all of that goes out. And then I get a charge that's 1.73 times 10 to the minus 8 coulombs. In tighter notation, this would be 17.3 nanocoulombs, and that's what the charge on the plates is. So now I want to go in and I want to look at a visual example. Okay. And this visual example is going to be in part B of this thing, which is going to look something like this. And we want to use an applet. So if you go into the lecture for chapter 5, you'll see that there's a link that reads PhET's Capacitor Lab applet. And that's what we want to use right here. So the first thing is that we should probably, let's just read this here. So we want to calculate the capacitance for the applets that they have. And what we're going to do here is that we're going to vary the plate separation between 10 millimeters and 5 millimeters and see how the capacitance compares. And then we want to change the area from 100 millimeters squared to 400 millimeters squared. So if I look at this, here's what we want to go in and look at. So I'm going to go in and do a different share. You'll see here is that the voltage is set to 1.5 volts. I have a plate separation of 10 millimeters. I have a plate area of 100 millimeters squared. And I can then come in here and say how much charge is on the plate. So that's how much charge. So what we want to do is that we want to calculate the capacitance for this. So let's take this information, and what we'll do here is that we want to calculate the capacitance, and we'll calculate it two different ways. So let's go do that here. And this is what we just saw right here. I know the charge, I know the voltage, so I can calculate this capacitance two different ways. Is that I just got to get some numbers here, and I'm going to say that this is my reference capacitance. So this is going to be the reference capacitance. So everything will be compared to this capacitor. And what we're seeing here is that we're going to again use the vacuum value, which is equal to epsilon naught, which we know is 8.85 times 10 to the minus 12 farads per meter. And you could see here is that the area in the situation is 100 millimeters squared, but we have to convert this into meters. So 1 millimeter is 10 to the negative 3 minus 3 meters squared. So that's 10 to the 6. So then this becomes 10 to the minus 4 meters squared. And then finally, we have our plate separation, which is then 10 millimeters, or we could write this as 0.01 meters. So now let's go calculate the capacitance. So we could now calculate the capacitance two ways. So the first way here is that we're going to say that our capacitance for a parallel plate capacitor using the capacitor equation is this value right here. So if I have that value, I'm going to take that value of the charge that's given, which is 1.33 times 10 to the minus 13 coulombs. Then I'm going to divide that by 1.5 volts. And when I compute this, I get 0.887 times 10 to the minus 13 farad. Now, the other way I can compute it would be the characteristics of the capacitor. So in this way, I should get the exact same answer if I use this relation instead. So if I then plug in my values again, and then the area here, the area is going to be 10 to the minus 4 meters squared. This will then be 10 to the minus 2 meters. And you could see here is that all of the meters go away, and I end up with a value of 0.885 times 10 to the 13 farads. So you could see that these values are comparable. So the question is, what does the applet say? So let's go share the screen again. And so what I need to do here is that all I have to do here is just tell it to show me the capacitance value. So if I click the capacitance, you could see that they're telling me to 2 sig figs that I have this guy right here. So if I just come in and I just snag that capacitance, you could see that the 2 sig figs, these guys agree. So if I copy this and I go back into my screen here, you could see that the value that's given here is this, and these values compare exactly. So for 2 sig figs, the value for CP P, which is Q over delta V, which is the same as epsilon A over D, we get 0.89, times 10 to the minus 13 farad. So it agrees with the applet quite well. So now what I want to do is that now I want to talk about variations. So that's our reference. So the first thing that we want to do is that we want to go in and we want to calculate some of these values if we change something. So now what I want to look at is that I want to say we want to decrease the plate separation from D equals to 10 millimeters to 5 millimeters. Now, according to the capacitance for this thing here, so according to this capacitance relation, we could then see that if I look at the ratio of the capacitance of the 5 millimeter to the capacitance of the 10 millimeter, this should give me, assuming I do not change the area or the dielectric, I'm then going to get a ratio that looks something like this. In other words, it should be 10 millimeters divided by 5 millimeters, so I should have a ratio of 2. Well, let's go calculate that. Okay, so the first thing I want to do is go back and share, and I want to decrease my separation. So I'm going to get rid of the capacitance. You could see that my separation has now changed. Now we could go in and start computing the numbers here. So there's 2 ways that we could calculate the capacitance. So the first one is just using the charge over the voltage here. Now note the charge has changed. So if I look at the charge, we could see that the plate's charge is here in the red, so that's 2.66 times 10 to the minus 13 coulombs. My voltage is still 1.5 volts. So when I calculate that number, I'm going to get 1.77 times 10 to the negative 13 farads. Now we've already done the calculation, so I'm just going to move through this quickly here. Now, if I look at it a second way, we could calculate it this way using this. The only thing that's changed here is the plate separation. But note, we already have the areas. The only thing that's changed here is just the value of D. So if I come in here, I still have 8.85 times 10 to the minus 12. My plate here is then going to be, what was it? Is it 10 to the minus 4 meters squared? So then this guy, which is 5 millimeters, is going to be 5 times 10 to the minus 3. And so when I compute this value, I also get 1.77 times 10 to the minus 3 farads. So both of these agree exactly the same. So what I want to compare now is that I want to look at the capacitance for a separation of 5 millimeters to the capacitance of D equals to 10 millimeters. And we've computed these values already. So the one for 5 millimeters is 1.77 times 10 to the minus 13 farads. The one that we just computed for 10, you can see that's 0.89 to 2 sig figs, but to 3 sig figs, it's 0.887 times 10 to the minus 13 farads. And so I get 1.996, which is, of course, equal to 2, which is exactly what we expected. So now what we want to do is that we want to increase the plate area from A, which is 100 millimeters squared, to 400 millimeters squared. So if we look at this thing, just like we talked about here, just using the capacitance equation again, so accordingly, to the capacitance, excuse me, of a parallel plate value, we could talk about one being 100. I'm sorry, let's just keep it like this. And then let's look at the ratio here. So we expect the capacitance of the 400 to be larger than that of the 100 millimeter. So then I could say that the capacitance of the 400 millimeter squared compared to that of the 100 millimeter squared should be directly proportional to the areas, where I keep the plate separation and the dielectric exactly the same. So all of these D's cancel out, just like this cancels out, and then we should get a ratio of 400 to 100, so it should be a factor of 4. So let's go calculate that value. So going back to here, I'm going to look at this thing, I'm going to get rid of the capacitance, and now I'm going to go back up to 10, and then I'm going to increase this guy. And then we need the stored charges, not the stored energy, the plate charges. So when I'm looking at that plate charge, it's telling us that it is the value of 5.31 times 10 to the negative 13 coulombs. So let's take this with us. Now I have this guy that I'm going to compute. So now I'm going to repeat, but this time I'm just going to put down the values here. So if I look at this, this is the capacitance of Q over delta V. You can see that the charge here is 5.31 times 10 to the minus 13 coulombs over 1.5 volts, and I'm going to get 3.54 times 10 to the minus 13 farads. So now, using the capacitance equation, the characteristic equation, putting in the exact same values that we just showed right here from the table, I immediately get 3.54 times 10 to the minus 13 farads. So again, if I look at the ratio of the 400 millimeters squared to the capacitance of the 100 millimeters squared, I get a value of 3.54 times 10 to the minus 13 farad. The one from the other situation, which is 10 to the 13 farads as well, gives me 4. So now if I just go in and I just grab that value, which I will not take you there, and just show you the capacitance, here's the value that I'll bring back. And here it is. You could see that that value agrees as expected.